Hello once again, this is presentation 7.4. The topic is confidence intervals and sample sizes. Let's begin. This material is contained in chapters 7 of your workbook and your textbook. Now this problem concerns a battery that's used in powering monitor equipment at a health center. And we want to find the details of the lifetime. A random sample of 64 batteries selected. The sample mean is found to be 284.6 hours. And for all intents and purposes, the sigma sub x is assumed to be around 9.6 hours. So let's see how the central limit theorem applies. We know that the distribution of sample means will follow a normal curve. The standard error is given by sigma sub x over square root of n, or 1.2. It's called the standard error. Coming over here now, we're saying that the probability of x bar being within 1.2 units of the population mean is 68%. Now we want to find the probability falling within 1.5. You see it on the screen there. And what we're saying is this 1.5, we have to measure that relative to this standard error up here, 1.2. So we take 1.5, divide by 1.2, and we get plus minus 1.25. And looking in the predictive probabilities, the area up to 1.25 is 89.44, and the area up to the halfway point is 0.5. So the area in between these two arrows here is 0.8944 minus 0.5. And we double it because it's a symmetric region, and that answer is 98.88% chance that the x bar will fall within 1.5 units of the population mean, which we don't know. The margin of error is given by 1.96 sigma square root of n, or 2.35, and we have it here on the screen. 95% of the x bars fall in that range, and the confidence interval estimate is given by your estimate plus and minus your margin of error. And you see those coming on the screen here. Your estimate x bar plus or minus your error term, which from up here, and of course that gives 282.24, 286.95, and we're 95% confident that this interval will capture the true population mean. The makers of the battery claim that the mean lifetime is at least 300 hours. What would you say in light of this information above? Don't believe it. And there we put in the interval, and this interval is this 282.24 to 286.95, and we're suggesting there's 95% chance this interval will capture that true population mean. Now we wish to examine the relationship between confidence intervals and sample sizes, so we're here talking about x bar again. The 95% error estimate, or margin of error, plus or minus 2.35. The 95% margin of error is given in the screen here, you see, and that pertains to this phenomena here. How large a sample size is necessary to find an estimate to within plus or minus 2. Now you see our error estimate up here is 2.35. We want to pull it down to 2.00, and that suggests if we pump up our sample size, this curve will narrow. So let's see how this is going to work. 99% margin of error given by 2.575. This is our error over here, plus or minus 2.0, and that suggests that this curve at the top is narrowed somewhat because of our increased sample size, a greater clustering, and there we have the z-score for 99% confidence. You see it coming on the screen here. This is our key formula. We manipulate these. N is this item squared, and if you work it out, n is 153. So in order to find an estimate of the mean to within plus or minus 2 hours, we have to pump up our sample size to n equal to 153. And there you have it on the far right here, a greater clustering to that degree. Now the quick and dirty rule goes as follows. If we have our error estimate here, if we divide the right side by 2, we divide the left side by 2, but under the square root, that 2 becomes a square root of 4. And if we want to cut the error term by 3, we have to pump up our sample size by 9, And generally, if we want to decrease our error, reduce our error by 1 over k, we have to pump our sample size up by k squared times n, and just above that you see k equal to 3. And that brings an end to presentation 7.4. We ask you that you review it again, take notes as required, and go to presentation 7.5.